We're going to start our lesson on gases by talking about pressure. First, we want to talk about what's happening in a gas. The particles are very far apart, and in fact, this is not to scale. The particles are much smaller than the space between them in real life. They're like point particles. So they're bouncing around randomly, very little contact. Although if you got two of them close together, they would be attracted. They're normally far enough apart that attraction does not matter. So what causes pressure? Pressure is caused by collisions. When the particles of a gas bounce against the container wall, that gives it a little push, and that's what gas pressure is. So if you have a container like a balloon and you push against it and you feel like that hardness, what you're really feeling is all those particles colliding against your hand. There are some different units we use for pressure. We abbreviate atmospheres, ATM. 1 atmosphere is about the pressure of the atmosphere. Of course, it varies a little bit each day, depending on the weather. Pounds per square inch, PSI, is another common unit, an English unit. Millimeters of mercury is similar to inches of mercury that you hear on the weather on TV. Just a different unit of distance. You need to know that there's 760 millimeters of mercury in 1 atmosphere. We use this conversion quite a bit. Technically, this number is not exact, but everyone treats it as though it is. It has enough sig figs that everybody just treats it as though it's exact, even though it looks like it has 2 sig figs. We treat it exact. So anyway, when we do our calculations, we'll see that. Another thing you need to know is that a millimeter of mercury is also called a torr. So particles pushing on the container wall cause pressure. Let's look at how that works. Let's start with just about 10. I'm going to put in 10 gas particles. I'm going to put this animation online. You have to have Java to run it, but this is how I'm changing things over here. I'm changing my settings. You can also add gas particles using this pump. Maybe I'll do that here in a second. Anyway, it's kind of fun to play with. You can waste time. I will warn you that. Anyway, so now I have some gas particles. Oh, I need to turn off the gravity. We'll turn that back on in a little bit. See how random they are. They have random motion. And if you want to see how the pressure is, I mean, you could read that, but let's look at just the bottom surface and notice how often it's being hit. Not real often. Sometimes it's hit harder than other times. Okay, so if we add particles, what's going to happen to the pressure? Let those randomize a little bit, and then of course the pressure is going up because look at the bottom edge and how often it's being hit now. It's being hit much more often, so the pressure is higher, and we can see that on our gauge. Pressure is caused by colliding particles. Let's see how a barometer works, and it will help us understand how atmospheric pressure works and better understand these collisions as well. Anyway, to understand how a barometer works, the best thing to do is to talk about how to make one. And the way you make one is that you have to have a dish or a pan or something full of liquid mercury. So liquid mercury in this dish. And we also have a glass tube that we fill up with mercury. This is not a straw. It has a closed end here, and it's totally filled up. And then you have to turn or invert the tube into the liquid without letting any air get inside the tube. This would be done by somebody putting their thumb on the end of the tube and then putting their hand down in the mercury and making sure that it's not released until it's under the surface. And they used to actually do this before they really understood the toxicity of mercury. School teachers would do this as a demo. But anyway, so when that tube is inverted into the liquid, something happens. Even though you don't let any air in, as soon as you put it in there, this level drops. And what's left in the end of this tube is really a vacuum. Vacuum means there's no gas particles bouncing around up there. This is totally empty, no molecules of gas in there at all. It doesn't all fall out though, it stops. And the reason it doesn't all fall out is that there's something pushing it, keeping it in. And what's pushing it is the atmosphere. The atmosphere is pushing down on the surface and kind of keeping it squished up in there. Okay. I know we sometimes think of a vacuum as this is pulling, and we think of the vacuum as pulling the liquid up, but that's not how it works. Gases don't pull each other. Gas collisions here are pushing the liquid up into the tube. It's sometimes easier to think about this backwards. What if I had a totally empty tube, nothing in it, total vacuum, and then I put it in the dish, the collisions on the container or on the surface of the mercury would push the liquid mercury up into the tube. Anyway, that's how it works. And this height, this difference right here, is a measure of the atmospheric pressure that day. You know, it varies a little bit each day, and so like 29 inches of mercury would be a typical pressure. So the higher the pressure of the atmosphere, the higher that column will be, the taller that column will be. And coming to understand atmospheric pressure, sometimes they talk about it as though there's a column of air that is pushing down on you. If you're down at sea level, there's this big weight up above you pushing down on you. I don't like that analogy because the atmosphere doesn't just push down. Gas molecules are moving in all directions, and so when you're down here, the atmosphere isn't just above you, it's actually pushing on you from all sides. Let's look at our animation again to kind of see how the gravity affects the atmosphere. Okay, let's put some particles in there. Let them randomize a little bit. Right now, this animation it's run on mathematical equations that give you random motion, and so the particles are moving around, bouncing around randomly. Right now, the calculation is not taking into account gravity. And so what I can do is I can come over here and turn up the gravity. So before we see the gravity, notice how the concentration of particles, it's always changing a little bit. Let me add a few more. You can add particles this way as well. Just pump some in there. There we go. The concentration of particles is pretty constant. I mean, it's always changing, but it's pretty constant, left to right, top to bottom. Okay, let's add some gravity and see what happens. Okay. Yeah. Okay, this is how the atmosphere looks. Here's the surface of the Earth. When you're down here, the concentration of particles is greater. So you have more particles bouncing against you from all sides. So this is like at sea level. If you go up into the mountains, the concentration of air is less because of gravity. And so there's lower pressure. Also notice that when you're at sea level, it's going to be easier to get some oxygen molecules to go into your lungs, right? But if you go up to high altitudes, there's less oxygen, so you're going to have to breathe harder to get enough oxygen. Anyway, that's how gravity affects the atmosphere.